Probably heard that the holy grail of physics research is a theory of everything. This is a theory of mythical proportions that would explain all particles and phenomena in the universe, an equation that would unite quantum mechanics with general relativity and reveal how all particles and forces manifest at the tiniest scales, and thus be able to explain all things. Stephen Hawking famously said that if we discover this theory, then we would know the mind of God. This has led to at least one physicist calling it the God equation. What gets lost in this narrative is that we already have a pretty good model that gets us a significant part of the way to an all-encompassing theory of everything. In fact, it is the most accurate theory we've ever had, and that is the standard model of particle physics. It describes all fundamental particles that we are aware of and 3 of the 4 known fundamental forces: electromagnetism, strong and weak interactions. It just doesn't include gravity. Now, don't let this simple chart fool you. This chart is just the most intuitive and visually appealing way to show something that is quite complex. There's actually complicated mathematical formulations behind the model that can take years of graduate level study to fully understand. It was developed by hundreds of scientists over several decades. But all that math can be roughly represented by this equation. This is the standard model Lagrangian. It represents the apex of human knowledge and understanding of how the universe works. Today, I'm going to explain the almost theory of everything in the most intuitive way that I can think of. So if you want to know how the universe works as best we understand it, you won't want to miss what's coming up right now. Before we get into the math, let's get a little more familiar with this chart. On the left, we have the fermions, and on the right, we have the bosons. The fermions make up all the matter that we are aware of, and the bosons are particles responsible for the 3 fundamental forces and the Higgs field. These are fundamental particles, meaning we don't know anything smaller that they could be made of. Ordinary matter that we experience around us is really just made of 4 of these particles: the up and down quarks, which make up the protons and neutrons in the nuclei of atoms, and electrons, which form a cloud around the nucleus, and a near massless particle called the electron neutrino, which is created during the fusion process in stars like the Sun. The other particles are rare and don't typically exist in ordinary matter. They're created inside particle accelerators like the Large Hadron Collider in Geneva, or from cosmic rays hitting the atoms in the Earth's atmosphere. They're very unstable and decay in a fraction of a second. It's a bit like on the periodic table, where some of the heavy elements bigger than uranium are also very rare because they tend to decay fairly quickly. The fermions can be further divided into leptons and quarks. The difference between quarks and leptons is that the quarks interact with the strong nuclear force, which binds the nuclei of atoms together, whereas leptons do not. The bosons on the right-hand side are the force carriers. The gluons carry the strong force, which binds the nuclei of atoms. The W+, W-, and Z bosons carry the weak force, which is responsible for some kinds of radiation. And the photons carry the electromagnetic force, responsible for all electricity, magnetism, and chemistry. Lastly, we have the Higgs boson, which is important for giving mass to all fundamental particles. It's called a scalar boson because the Higgs field has a value at each point in space, but no direction, unlike the electromagnetic field, which has both a value and a direction. The standard model is actually represented by a complex set of equations, but we can simplify all this and write it in one equation known as the standard model Lagrangian. Don't get intimidated by how complicated it looks, because I'm going to explain this intuitively. A Lagrangian is just like the sum of all energies. Remember that Einstein's equation E = mc² says that mass and energy are equivalent. The entire universe can be represented by the mathematics that accounts for energy. That's what the Lagrangian is. It's important to understand that the standard model is a quantum field theory. This means that when I say fundamental particles, what I mean more precisely is that these are really an excitation in a quantum field. It's not like a tiny marble, but like a tiny wave. So for example, an electron is an excitation in the electron field. A photon is an excitation in the photon field, and so on for all the particles that you see in the standard model. The first term is composed of two matrices, F sub mu nu and F superscript mu nu. Normally, F represents only the electromagnetic field strength tensor, but in the context of this simplified equation, this term represents all the ways that all the force-carrying particles, the bosons, interact with each other. Only the Higgs is not included in this term. Mu and nu are just indices that represent the four components of spacetime, the three spatial dimensions and one time dimension. If this term was more fully expanded to show the interactions of the individual bosons, this is what it would look like. The first term with B sub mu nu roughly represents the field of the electromagnetic force. The W sub mu nu A matrices represents the field of the weak force, and the last term, G mu nu A, represents the fields of the strong force. The A and the W matrices represents an index that takes into account, roughly speaking, the three different weak force bosons, W plus, W minus, and Z. The A in the G matrices represents an index that takes into account the 8 different color gluons. There is no A present in the B matrices because there's only one photon field. Photons don't interact with each other, unlike W, Z, and gluons, which do interact with each other. So the matrix is less complicated for electromagnetism. We can see this more simply in Feynman diagrams because these diagrams represent the mathematics of these interactions in a much more intuitive way. So gluons, for example, are color charged and can have a 3-gluon vertex or a 4-gluon vertex. A Z boson or a photon can result in a W plus and W minus boson, or a W plus and W minus boson can annihilate to create a photon and Z boson. The next term in the simple Lagrangian refers to the fermion fields and their interactions with the gauge fields. Simply put, it describes how matter interacts with forces. This term, when more fully written out, would look something like this. So what's going on here? First, you'll notice there's a factor I in these terms. This is the imaginary number defined as the square root of -1. Imaginary because you have to imagine that it exists. You might ask, why do we have imaginary numbers in physics in the first place? The short answer is that it's a mathematical tool that allows the use of more numbers. So we're not constrained to only use the simple real numbers. This is allowed in physics as long as your final result representing physical values does not contain imaginary numbers, because that would indicate that something is wrong because it is not physical. So using imaginary numbers is fine as long as they don't end up in the results. The term Q and Q bar just refers to the quarks and antiquarks. Furthermore, we have this gamma mu, d mu, which couples the quarks to the force fields. In other words, it represents how the quarks interact with the electromagnetic, weak, and strong force. And this is summed up over all the 6 different quarks of the standard model. The next 2 terms contain and represent the leptons, specifically left-handed and right-handed leptons. Particles have a property where they are either right-handed or left-handed. Right-handed means that the spin of the particle is in the same direction as the motion of the particle. Left-handed means that the spin is in the opposite direction of motion. It's important for leptons because it turns out that only left-handed neutrinos exist, but electrons and its heavier cousins, the muon and tau particle, can be both left or right-handed. So the two psi L and psi R terms represent the interactions of the left and right leptons, which is not quite the same. Just like with the quarks, we sum over the different particles, and we also have the part gamma mu d mu here that represents the interactions of the leptons with the 3 forces. These 3 terms form the fermion Lagrangian, which gives us the Feynman diagrams for how the matter in the universe interacts with the forces in the universe. The gluon is very simple as it only interacts with quarks, and the neutrino only interacts with the weak force, and all other particles except neutrinos interact with the electromagnetic force. The next 2 terms are related to the Higgs mechanism. The first term describes how the force-carrying particles interact with the Higgs field. This term represents the part that gives mass to the weak force particles, the W plus, W minus, and Z bosons. The second part gives us the interactions of Higgs with itself. The first part contains d mu, which represents the gauge bosons. Psi and psi dagger represent the Higgs field. Thus, this term couples the Higgs to the gauge bosons. In practical terms, however, this only applies to the weak force bosons as they are the only bosons that have mass. Photons don't obtain mass by the Higgs mechanism and thus are massless. Gluons, the strong force carriers, are massless because they do not couple to the Higgs field. So in short, this represents the Higgs mechanism giving mass to the weak force bosons, W+, W-, and Z bosons. This leads us to the following Feynman diagrams with the Higgs boson interacting with the weak force bosons. The first Feynman diagram, for example, shows two W bosons turning into a Higgs boson. The second diagram shows two Z bosons turning into a Higgs particle. The second part of the equation represents the Higgs potential. Higgs is the only field in the Standard Model that has a potential. The Higgs field lies at the value of the minima, which is non-zero, and this in turn gives mass to particles that interact with it. This potential not only gives mass to matter particles, but also to itself. The Higgs boson itself has mass. In terms of Feynman diagrams, this term gives us the different self-interactions of the Higgs boson, a bit like what we saw with the gluons of the strong force. The potential in the term is what is responsible for mass, but the next term in the Lagrangian describes mathematically how matter particles interact with the Higgs field to obtain mass. This term actually hides three terms. Thus, actually, we would write the following. The subscripts R and L again refer to the left and right-handed particles. The gamma represents the Yukawa couplings of each particle to the Higgs field. Yukawa coupling just describes how strong the coupling of individual matter particles is to the Higgs field. The stronger the coupling, the higher the mass that the particle acquires. Phi represents the Higgs field. Now, to be more specific, the first term is the leptons and how they couple to the Higgs. The second term is the down-type quarks, such as down, strange, and bottom quark, and their coupling to the Higgs field. The last term is the up-type quarks, thus the up, charm, and top quark, and their couplings to the Higgs field. These terms are physically important because they connect the fermions with the Higgs and result in masses that the fermions have. In terms of Feynman diagrams, here's what some of these would look like. For example, a Higgs can decay into a tau and anti-tau pair. Finally, the last term is this HC term, and that just means Hermitian conjugate. While the prior term describes the interaction between a Higgs particle and matter particles, the Hermitian conjugate describes the same interactions, but with antimatter particles. We have to take antimatter particles into account in this Lagrangian because they also exist. Technically, there would be other HC terms in this Lagrangian as well that would describe how antimatter particles interact with forces. Thus, if we combine everything we just discussed, a more expanded Lagrangian would look like this. But you have to keep in mind that even this is a shortened version of what all the equations expanded out fully would look like. But for now, the shortest version looks like this and what the various terms represent. If simplified to its essence, this is really describing what almost all the universe is made of, as we understand it today. The first term is how the quantum forces of the universe interact with each other. The second term is how matter interacts with all the forces. The third term is how force particles gain mass. The fourth term is how the Higgs interacts with itself. The fifth and sixth terms describe how the matter and antimatter particles gain mass. You should know that although this is the best and closest thing we have to a theory of everything, it has some problems. One of the biggest gaps, of course, is that gravity is not accounted for. And the other big problem is that dark matter and dark energy, which scientists believe make up about 95% of the universe, is not in this model. So there's plenty of work to be done. Check out this video by the online Blackboard where they go deeper into the Standard Model and some of its problems.